Wankel engines were first invented in the early 1960s by German engineer Felix Wankel. Since its inception, the Wankel engine saw an increase in displacement and even the addition of turbocharging. Wankel engines, specifically the series of rotary engines produced by Mazda, had a reputation for being relatively small and powerful, but at the expense of poor fuel efficiency. The engines became popular among automotive circles and were even used in light aircraft because of their low mass, compact size, and tuning potential. Its popularity was attributed to the inherently high power-to-weight ratio that rotary engines offered. Mazda first put the engine into production with the release of the NSU Ro80 and the Citroën GS Birotor between 1967 and 1977 as part of a partnership among the automakers. Despite the initial hurdle the early cars had with reliability, the rotary design was subsequently used in a slew of successful models under the Mazda name, like the Cosmo, RX-3, and 3 generations of the iconic RX-7. For this reason, the rotary design has been praised as a competitive engine and even developed a cult following amongst car enthusiasts. And as rotary engines became a common entry into motorsport events, racing authorities ran into the problem of representing each engine's displacement correctly. This was attributed to the unique design of the rotary engine since they are variable volume, progressive cavity systems. Since each rotor has 3 faces, and each face has 3 cavities of volume per housing, each face of the rotor sweeps its own volume as the rotor orbits within the housing. Each side of the rotor is brought closer to and then further away from the wall of the internal housing, compressing and expanding the combustion chamber. The rotor itself is comparable to a piston, and much like a reciprocating engine, the rotary design is an internal combustion engine that employs the same 4 stages: intake, compression, combustion, and exhaust in each cycle. But when the cylinder volume changes as the piston travels up and down in a cylinder, the volume, configuration, and position of the operating cavity changes as the rotor orbits in an eccentric fashion. And since a rotor has 3 faces, the same process is repeated continuously. Looking closely at the rotor, this becomes evident. When side A is about to be propelled by the exploding gas, side B is in the intake and compression phase. While this is happening, side C is in the exhaust phase. When the rotor moves, side A goes into the exhaust phase, and then side B begins expanding. Side C begins the intake and compression phase. Furthering frustration on how to represent a rotary engine's displacement correctly is that the rotor travels 1/3 the speed of its crankshaft. Subsequently, its output shaft travels faster than that of the rotor's oscillating parts. This perceived advantage caused many regulatory bodies in automotive racing to variously consider the rotary engine to have the equivalence of a reciprocating 4-stroke piston engine of 1.5 to 2 times the displacement of 1 cavity per rotor. So rather than enforcing a rule to divide quoted displacement for participants driving reciprocating piston engines, most racing organizations simply decided to double the quoted displacement of rotary engines. It should be noted that the scope of this video is not to conclude whether doubling the displacement is best practice, but rather understand the underlying difference between a reciprocating engine and a rotary engine. To better comprehend how this was done, let's first understand how to calculate displacement for a piston engine, which is swept volume multiplied by the number of cylinders. Since the number of cylinders are obvious, we will shift our focus on swept volume, which is the displacement of 1 cylinder between the top dead center and bottom dead center. In effect, the piston would sweep its volume as it travels in the engine cylinder. But to keep things simple, we won't go into detail on how to actually calculate swept volume. Conversely, calculating the swept volume for a rotary engine replaces the number of cylinders with the number of rotors. As an example, Mazda rates their 13B rotary engine at 1.3 liters. Each face of a single rotor has a swept displacement of 654 cc's, or about 0.65 liters. This is then multiplied by the quantity of rotors, in this case 2, resulting in 1.3 liters. However, using this calculation as a relatable number to compare a 4-cycle engine to a rotary engine is not optimal. The number of rotors alone is not enough. If we're going to use the number of cylinders versus the number of rotors, we should instead need to factor in the 3 phases of each rotor as well, and how many phases complete a thermodynamic cycle within a certain number of degrees. A thermodynamic cycle is a series of actions that involve the transference of heat into and out of a contained system, and the changing pressure, temperature, and other variables that eventually return the system to its initial state. Though the stages of a thermodynamic cycle are the intake, compression, combustion, and exhaust strokes, our primary consideration will be the completion of a thermodynamic cycle. In a piston engine, the crankshaft is directly tied to the reciprocating motion of the piston. One thermodynamic cycle equates to 2 revolutions or 720 degrees of the crankshaft of the 4-cycle engine. On the other hand, a rotary engine's crankshaft rotates 3 times faster than that of the rotor. Because of this unique gearing, and because a rotor has 3 faces, each offsetting face is in a different stage within its respective thermodynamic cycle as the rotor orbits. The implication is that a rotor's face will be brought through the stages of its respective thermodynamic cycle more frequently than a piston, in such that the completion of an entire thermodynamic cycle occurs twice as frequently as a piston, or at a 2-to-1 ratio. Simply put, when the piston completes its entire thermodynamic cycle at 720 degrees, a rotor's face has completed it twice. At this point, it may seem the reason why racing organizations decided to double the quoted displacement of rotary engines was possibly justified. Moreover, the defining moment of the rotary engine and Mazda was the 4-rotor 26B, which was used only in various Mazda-built sports prototype cars, which included the 767 and the 787B. The 26B had 2.6 liters of displacement and developed 700 horsepower at 9,000 RPM. But what made the 26B remarkable was that it used variable geometry intakes and an additional third spark plug per rotor in its design. In 1991, the 26B powered Mazda 787B became the first Japanese car and the first car without pistons to win the 24 Hours of Le Mans. Despite the success, the last car powered by a rotary engine was in the 2012 RX-8 production run. But largely because of poor fuel efficiency and emissions, the RX-8 was abandoned, which further frustrated any uptake in the RX-8's development. However, Mazda has continued to work on developing the technology as it is one of the company's signature features. On occasion, Mazda officials have suggested that if the rotary engine can achieve similar performance of a reciprocating engine, they would reintroduce it to power a sports car under the Mazda name. On October 27, 2017, senior leadership from Mazda told journalists that they were still working on a rotary engine for a sports car that will potentially, in some markets, work in conjunction with hybrid drivetrains, but both will have distinct powertrains from Mazda's first electric vehicle, which will be released sometime in 2020.
We be rolling. We be rolling. We be rolling deep. We be rolling deep.
If you like this kind of content, give it a thumbs up and leave a comment. Also follow me on Instagram, link in the description below.